talking about enhancing portfolio optimization with the PCR technique. So the project sponsor is Hamilton Lane. The Hamilton Lane is one of the largest private market in investment management firms globally, and providing a solution to the provide private wealth investors around the world. So let's talk about the goal of this project. The main idea here is to build an optimized portfolio that leverage principal component regression, or we call it PCR. The focus is to explore a practical way of applying PCRs in solving the issue of the multicollinearity in portfolio optimizations. So next, we move to the portfolio optimization. As an introduction to those who are not familiar with this technique, this is all about balancing risk and return, and it's a fundamental technique in finance that helps align investments with specific goals and constraints. Essentially, it shows how we make sure we can manage the risk and return for the portfolio. For this project, we applied the optimization model to construct a portfolio that leverage factors like momentum, quality, value, size, and minimum volatility factors. And we will talk about those models in later slide. So now let's move to the PCR and PCA. So what are those? So PCR is the principal component regression, and it's essentially a combination of two things: principal component analysis and the linear regression. It's a method that helps deal with the messy correlated data, or like a high dimensional data set in portfolio optimization. The PCA's job is to take a set of potentially correlated variables and reduce them into uncorrelated components, which we call principal components. These components capture the maximum variance in the data, so we are retaining the most important information while simplifying things. This approach is particularly effective when dealing with the multicollinearity, when variables are too correlated for straightforward regression. So this chart on the right shows how a PCA simplifies a 2-dimensional data set by breaking it down into two main principal components. And this makes the regression models more stable and reliable. As for the challenge that I want to take, to this issue of multicollinearity, so I think it is really a big challenge in portfolio optimization. It happens when the factors we use to explain stock returns, like momentum or quality factors, those are too correlated with another one. This can undermine the accuracy of our optimization model, because it becomes hard to figure out which factor is actually driving the results. What's worse is that it can lead to portfolios that are overly concentrated in a few assets, making them less robust and more vulnerable to market changes. So addressing multicollinearity is crucial to building portfolios that are stable, diversified, and aligned with the modern portfolio theory. This is a problem that I want to do it in a practical way. So first, here's a quick look at the data processing that we want to prepare for the later analysis. So first, we define the data range for the data from January 2021 to December 2023, and selected the tickers for both assets and factors. You can see this list on the left, where the factors include things like momentum, quality, those risk factors. So after gathering the data, and it calculates the daily percentage change for both factor and assets. This gives us the X in the code, and which represents the factor returns, and Y, which represents the asset return. The table on the right shows a sample of the process data. with percentage changes for each factor over the selected time range. This step ensured the data was clean and ready for further analysis and setting the stage for the PCA regression and optimization. So now let's talk about the specific models of the optimization model. And so this is a model used in the project. For the core part, the model aims to maximize the Sharpe ratio, which measures the return per unit of the risk. The formula here shows that I can finding a portfolio weights that maximize the ratio of expected return to risk, subject to constraint like weights summing up to 1 and being non-negative. On the right side is the factor model that I'm using in this project. The equation here, the alpha is the vector of the intercept term, B is a matrix of vector loadings, and F is a vector of vector returns. The epsilon is the error terms. This ensures we are incorporating the factors efficiently into our portfolio. For the implementation, I use the Riskfolio library, which simplifies the complex optimization tasks like this. And the code here shows how we set the parameters for the model, specifying the risk, measure, objective function, and other details. And let's move to the PCR. So there's a framework on my PCR that I apply into the Riskfolio library. The main idea here is to apply a principal component analysis to the factor returns. So denoted as the F here, to reduce the dimensionality. This allows us to retain only the components that explain most of the variance. For this case, I set up the percentage as a 95%. The formula at the top, so F decomposed into the ZP plus the residential arrow. So Z is represents the principal components, and the P for here is like the right side is the loading matrix. So you can see the code looks like in practice. By using the Riskfolio library, we calculate the loading matrix, and that which shows how each principal component contributes to the factors. The heat map below here is the loading matrix and shows a clear visualization of these contributions, and also highlighting the relationship between the ISET and the factor of the dimensional reduction. So this step makes the optimization process for more robust and efficient.